In the last few lectures, we have talked a lot about signals, defined some signals, looked at properties of signals, and things like this. Now let's talk about the other important component of this course, which is that of a system. So in this video, I'm going to try to give you some examples and try to define what we mean by a system in this class. The word system seems to have a different meaning, and different people think of a system as different things. In fact, when I looked at the dictionary definition of system, I got quite a few different definitions. Okay, we are going to use this word system in a very specific way in this class, and essentially what we are going to think of as a system is as a process which transforms input signals into output signals. So it's a fairly general description, and think of it as follows. So think of it as we have a black box. The input to this black box is a certain signal. So this signal is x of t. And this signal, or the input signal, causes a certain output from the system, or causes the system to respond in a certain way. And what do we mean by a certain way? There is a certain signal at the output of the system, and we're going to call this as y of t. Okay, the system defines a relationship between x of t and y of t. So when I specify a system, what I mean is I give you enough information for you to be able to find the output signal y of t for every input signal x of t, and there is some relationship between y of t and x of t. Similarly, in the discrete time case, we could say that the input is a signal x of n, which produces an output from this system, which is another signal y of n. Okay, as you can see, this is a very broad definition of a system, and a lot of things can be thought of as systems under this framework. And to some extent, it is intentional to define the system in such a general way, because some of the tools that we are going to develop to analyze systems and understand systems are actually applicable to a lot of different systems. Things that you may see in electrical engineering and signal processing, communications, mechanical engineering, chemical engineering, so on and so forth. And so we want to sort of provide a general mathematical description of a system which applies to all these different areas. Okay. What I will do is this: I will try to give a couple of examples of what systems might be, and I think it will help you understand what we are talking about a little more. So the first example I'm going to talk about is something which you are all very familiar with and you're using every day. In fact, I should say that these are things that now students are using even in the classroom when they should not be using them. If you haven't guessed what I'm talking about already, I'm talking about cell phones. Okay, so think about, I'll give you a quick description of what happens when somebody talks on the cell phone. Let us say you're talking to your friend on the cell phone, and let's just think about the wireless link from the cell base station to the cell phone that you actually have. So what happens is this: we have a cell base station. This transmits an electromagnetic signal. Okay, so there is an antenna here, and this transmits an electromagnetic signal. Let us say this is a signal x of t, and you have your cell phone somewhere here. So I'm trying to draw a smartphone here, so these days you don't see any antennas sticking out of the phones and things like this. So here is a cell phone. It has an antenna that's just not visible. So what could happen is this: you may be inside a room, and so you may not actually have a direct path for the electromagnetic signal to arrive at the phone, right? So but what typically happens is this: you have reflectors. So you may have a big building here, and then there could be one path from the transmitter. This is the transmitter, and this is the receiver. Could be a reflection from this building. Now you may have another reflector here, let us say, and this signal will also arrive at the receive antenna. And you may have several such reflections, but let's just focus on any one of these paths. Okay. Now notice that this path has to travel a certain distance. Let us say this is the first path, so it travels a distance of d1. Now because this path has to travel a distance d1, if I transmit the signal x of t from the transmitter, it's going to take some time before it arrives at the receiver, right? It's going to take a time, let's call that as tau1, and this is going to be d1 divided by the velocity of light. Let's call that c. So this is going to be the time delay associated with this path. Now what that means is this: if I looked only at the first path, if I transmit the signal x of t, what I end up receiving is actually x of t minus tau1 at the receiver. And in fact, what might happen is there could be some kind of attenuation when because it got reflected, and because of the fact that the receiver is farther away from the transmitter. So let's model all that together as saying there is some attenuation with this path, and let's call that as h1. So what I will really receive is h1 times x of t minus tau1. Now because of the fact that I may have another path, there could be an attenuation h2 associated with this path, and there could be a time delay tau sub 2 associated with this path. When these two paths arrive at the receiver, what's going to happen is they're both going to add up together. So what I may actually end up receiving is the signal y of t. In the interest of clarity, let me erase all these things. Just call this as tau1. So what I may really end up receiving is this signal. Okay. So what I could do is this: I could abstract the physical phenomena that happens in the channel into a black box, and I could say the wireless channel at this point is behaving like a system. The input to this system is the signal that's transmitted by the base station x of t, and I have a system which produces the signal y of t. Y of t is related to x of t, right? Because y of t is h1 times x of t minus tau1 plus h2 times x of t minus tau2. So this is the signal y of t. Notice that there is a clear relationship between x of t and y of t. If we knew h1 and tau1, then we could compute y of t for any given x of t. So this is a system now. Okay. Now I want to emphasize something here, and this is actually a very important point. This is actually a note about terminology, but I think you should think about this a little bit because this may clear a lot of confusion later on. I have mentioned this before and I will do it again. X of t and y of t are both are used. Let's just talk about x of t. Let's say x of t is used to refer to two things here. Okay. One, it is used to refer to the entire transmitted signal. Which means in this case this could be an actual waveform. Right? This could be a speech waveform that we actually transmit. it is also used to refer to the value taken by this waveform at a particular time. The reason I say that is this. Look at what this means. You can think of it as two ways. One way to think of it is it's x of t shifted by tau 1 seconds to the right, and this is x of t shifted by tau 2 seconds to the right. But another way to think about it is that if I want to find the value of y of, let us say I want to find the value of y at 2 seconds, I could do this by computing h1 times x of 2 minus tau 1 plus h2 times x of 2 minus tau 2. What that means is this: if I want to, let's say this is time 0, this is time 2, if I want to figure out the value of y here, I take two previous values of x. Say this is x of 2 minus tau 1, and this is x of 2 minus tau 2, and then I take a combination of them in order to produce one value of y of 2. But I need to do this for all values of t. That's why there is a relationship between the entire signal y of t and the entire signal x of t. Okay, so we will be using x of t and y of t to denote both the signal as well as values taken by the signal at specific times. And personally, I would have preferred to always use some notation like this to denote the entire signal, as opposed to just x of t, which could denote the value taken by x at a specific time. Unfortunately, books do not do this, and after you take the class, you may have to read books on your own, and so I do not want to introduce my own notation and confuse you, so we'll stick to the notation that is typically used in books. Okay, all right, so that's that. Now let's look at this example. Let's come back to the cellular example, and let's look at what kind of problems are we typically interested in such an example. So what's the ultimate goal for us? The ultimate goal in a typical cellular system is we take the received signal. This is the received signal at the antenna. And what I would like to do is this. What I would like to do is to take this signal, do some processing on this signal, and be able to get my x of t back, or at least an approximation to x of t back, so that I could run this signal through a speaker and then you can listen to it. Now this can also be thought of as a system, because this system has an input which is y of t, and it has an output which is x hat of t. Okay, typically in such an engineering example, we are interested in a few different things. The first one is, if I want to design this system, this is at the receiver. I can call this as receiver signal processing. In order for me to design this system, what I first need to understand is the precise relationship between y of t and x of t, which means I need to know the parameters h1, tau 1, h2 and tau 2, so that I can try to process y of t and try to get x of t back from y of t. Okay, so this could typically be called as a system identification. The point is that there are parameters of the system. The output of a system depends not only on the input, but it also depends on certain parameters of the system, and we want to identify these systems. These parameters, or parameter identification or estimation. Okay. Actually, the way it works in cell phones is quite interesting. What they do is periodically the base station and the receiver, the base station have an agreement. They don't periodically have an agreement. They have an agreement for the base station to periodically send a known sequence. So the base station periodically transmits an x of t that is known to the receiver. So the receiver expects to get x of t, but in fact it observes what it gets. It gets a certain y of t. From this, it tries to estimate what h1, tau1, h2, and tau2 are. So that's the first stage. That's called system identification. And then what we may be interested in is an analysis. That may involve understanding exactly what has happened to x of t. How has x of t been modified by the system, which may allow us to do some processing. Okay, so this we can say is understanding the effects of the system. Sometimes this can be used to invert, or I should say ultimately the goal is to get x of t back from y of t, right? So this may be used to further process y of t or invert. When I say invert, I mean the process of getting x of t back from y of t. Okay, so now you can see our description of a system as being something that just transforms an input signal into an output signal is general. It applies to the channel. It also applies to what processing you actually do on your cell phones as well. So this is yeah, so I think I mean the point I want to make is that this view is a very general view that will be very useful. Since this idea of a system is really important, I'm going to give you a very simple exercise to make sure that you understand what we're talking about. If you think you understand what I'm talking about, you can kind of fast forward this part of the video. Um, if not, I think if you're not entirely clear what I'm talking about, it may be worthwhile to do this exercise. Suppose we consider the previous cell phone example. And if I told you that the parameters of the channel, let's say h1 is 1/2 and a delay is, let's say, 1/10 of a second. That's actually a very large delay, but just for the purpose of example, I'm going to say this is the delay. Say h2 is 1/4 and tau2 is 2/20 or 1 over no, I'm sorry, 2/10 or 1/5 seconds. Okay, suppose my input x of t is the signal. Let's say it's between 0 and 1 and it has the value 1. Think about what will be the output y of t. Okay, I think you should, if you think you can do this, you can fast forward, quickly get through it, but if not, you should stop it, try this yourself. Yeah, I'll take a small pause here because I'm going to work this out. Okay, so there are a couple of ways to do it. Like I said, one way to do it is to say first form x of t minus h1 times x of t minus tau1, which will be will have a height of 1/2. Maybe I will draw it to scale, or try to draw it to scale. Then I could take h2 of x of t minus tau2, which would be, say it starts at 2, oops, draw it to scale. So it's probably like this. Starts at 2/10 and goes up to 12/10. So the received signal will be the sum of these two. So between 1/10 seconds and 2/10 seconds, it has the value 1/2. And then it goes up to 3/4. So this is 1/2. This is 3/4. And then it comes back to 1/2 at 11/10. I'm sorry, it comes down to 1/4. So this is 1 over 10, this is 2 over 10, this is 11 over 10, and this is 12 over 10. The height here is 1/4. Okay, zeros here. So that would be the received signal. I hope it makes sense. You can even verify by plugging in some values of t that you actually get y of t to be equal to h1 times x of tau, t minus tau 1 plus h2 times x of t minus tau 2. Okay, now let's consider another example, another everyday example, which is that of driving a car. And we can try to model the car as a system by considering the input as the force that you apply on the gas pedal, and if you're interested in, say, observing how the car travels, or the position of the car as the output. Okay, I will just do some simple assumptions here, and we'll try to get a relationship between y of t and x of t, just for the purpose of saying that these things can be modeled in the same framework of a system that we have as well. So let us say that m is the mass of the car, and let us say that applying a force of x of t in the gas pedal is equivalent to applying a force of c times x of t. So the force is like pushing the car with a force of c times x of t. Okay, and let us so the velocity then at time t will be the derivative of y of t, and the acceleration will be the second derivative of y of t. Okay, and let's say we have some friction, and so the friction force is, say, rho times the velocity, force due to friction. Okay, so which is then rho times the derivative of y of t. Okay, then we have the total force that's applied on the vehicle is c times x of t minus the force due to friction, which is rho times the derivative of y of t, and this must be equal to mass times the acceleration of the car. Okay, now you see that you get a relationship between y of t and x of t, but the relationship is actually given in terms of a differential equation that relates y of t and x of t. So to be more precise, we could write this as m times the second derivative of y of t plus rho times the derivative of y of t is equal to c times x of t. So this now specifies a relationship between y of t and x of t as well, right? Now in the but you see, this is not as direct as plugging in values of x of t and finding values of y of t. You actually have to solve this differential equation in order for you to find the y of t for any given x of t. But nevertheless, if m, rho, and c are given to you, you could solve the differential equation, assuming that you can solve this, in order to find y of t. Okay. Now, in this problem, typically what we may be interested in is in one of a few things like this. Typically what we want to do is we want to control the force in such a way that we get to a certain position at a certain time, right? So what we typically have is this: we have constraints on y of t. We would like, say, I would like to get to my office in 10 minutes, or at 10 minutes I want to be at my office. So if I think of my a road between my office and my house as a straight line, if my house is the origin, then let's say my office is at 5 miles away from my house, then I would like to be at 5 miles at y of 10 minutes, right? And further, I would like to park my car there. So not only do I want to get there, I want to make sure my velocity is 0 as well. And I'm a law-abiding driver, so I would like to make sure that y of t never really exceeds the speed limit for all values of t between 0 and 10 minutes. So what I would like to make sure is that if I plotted y of t, it never really goes more than the speed limit of 100 miles an hour. I'm just kidding. 50 miles an hour. And then once you get closer to the university, 35, or inside the university, 10 miles an hour. Okay. Now that's so the point is this: a typical application we are interested in here is this is what can be called as a control application. So what we would like to do is this: we would like to change the force or the input. So what we would like to do is we would like to change the force in a way that we get a desired signal y of t. So typically how this is done is there is a desired y of t, and depending on the difference or the error between these two, we typically control the force. Okay, so typically what happens is once you get close to the destination, you look at where you need to be, and that's the error. So you know kind of how far you are away, and then you apply a force to your gas pedal such that you will go and park in the right place. Okay, so this is another example. So in this case, we could define this as the system, and this is actually the control that would change the input in order to make sure we get a desired output. So I want to emphasize two things from here. First, sometimes the description between the input and output may be through a differential equation. Now you may have seen LRC circuits, RC circuits, all these kinds of circuits where voltages and currents, or voltages across certain components and applied voltages are related through differential equations, so on and so forth. Okay. So the point is sometimes they may be related through differential equations, and what we may be interested in is in controlling the input in order to achieve a desired output. Okay, I think with these two examples, hopefully what we mean by a system is clear. I will just do one more example of a discrete time system, just to give you an idea of a discrete time system. And even this, I would suggest that you can try to play this in twice the speed, see if there is anything new for you. If not, you can continue to quickly get through this. So one example of a discrete time system I thought I would give is a bank. Okay. Let us say that x of n represents the amount of money deposited in the nth year, or let's say nth month, and y of n says your balance at the beginning of the month. Okay, and let us say r is the interest in percentage that you get per month. Okay. Then you could write a relationship between x of n and y of n as saying, what is y of n? Y of n is, there are two ways to write this. One way to write it is as follows. You can say, well, I had y of n minus 1 last month, and then this generated an interest of r%. So now this is worth y of n minus 1 times 1 plus r over 100. And in addition to that, I added x of n more dollars to my bank account. Right? So this is one way to describe the relationship between the output y of n and the input x of n. Okay. Now notice this also, this is not at least the way I've written it here is not a fairly straightforward relationship between x of n and y of n, but I have to compute y of n recursively, in the sense, if I give you a signal x of n, if I told you that there was this person and this person deposited this much money every month, so if I told you this person deposited, $500 the first month, 300 in the next month, 250 in the third month, so on and so forth, then what you could do is you could figure out y of n based on x of n. But the way you would figure it out is to first compute y of 1, which would actually be equal to x of 1, and then you would compute y of 2 based on y of 1. You would take y of 1, multiply it with 1 plus r over 100, add x of 1 to it, so on and so forth. But if you think of the system as operating on the signal x of n, for any given x of n, we can find the signal y of n. Right? So this is what I mean by by saying that the bank can be thought of as a system. Okay. There is another way to write the input-output relationship too. It's just a little more messy than this. You could also think of it as y at time n is, let's say, how much ever money you put in the first month times 1 plus r over 100 raised to n minus 1, because this is the total amount of money that would be available due to your deposit in the first month, plus x of 2 times 1 plus r over 100 raised to n minus 2, so on and so forth, until x of n minus 1 times 1 plus r over 100 plus x of n. Right? So notice this, if you were to use this to compute your y of n, it's fine. You don't actually have to use y of n minus 1 to compute y of n, but you would be repeating, or this would not be a very efficient way to compute y of n. Okay. Good. I think I will stop the video here.